I am Vignesh. My roll number is 23VV1A1244. Today I will present my project on real-time cloud infrastructure monitoring and log analytics system. In modern cloud computing environments, monitoring systems generate massive volumes of telemetry data every second. Imagine a data center with thousands of servers, each server producing logs, CPU metrics, memory usage statistics, and disk I/O measurements. My project addresses this challenge by implementing and evaluating 7 advanced tree-based data structures specifically designed for cloud monitoring workloads. I processed 6 lakhs log records, handled 2 lakhs 50,000 metric queries, and performed 2 lakhs dynamic updates to determine which data structure performs best under the real-world conditions. The several structures I implemented are AVL tree, red black tree, splay tree, B-minus tree, B plus tree for indexing, and segment tree and Fenwick tree for range analysis. In this project, I used 3 real-world datasets: logs, 6lakhs.csv, several logs containing timestamps, security levels, info, warning, error, critical, and log messages. The second dataset is metric queries, 2,50,000.csv. System metrics: CPU uses, percentages, memory utilization, disk I/O statistics. And the third one is metric updates 2lakh.csv, dynamic updates, real-time metric changes, counter increments. The system was implemented in C++11 using MinguW GCC 6.3.0 compiler with O2 optimization on Windows platform. I used higher resolution chrono timers for precise measurements and implemented progress indicators for long run. Let me explain each data structure I implemented. Self-balancing binary set trees are used for indexing. The AVL tree maintains a strict balance factor guaranteeing big O of log and height but requires rotations during insertion. The red-black tree uses relaxed balancing with color properties resulting in fewer rotations. The splay tree is self-adjusting every access node moves to the root. Multi-way trees optimized for disk-based storage. The B tree has a high branching factor that minimizes the height and disk accessions. The B plus tree stores all data in leaf nodes linked together, making range queries. Range query structures specialize in analytics. The segment tree supports big O of log n range queries and point updates on static arrays requiring big O of foreign space. The Fenwick tree, also called binary index tree, provides big O of log n operations with only big O of n space overhead, making it memory efficient for cumulative frequency tables. Now coming to benchmark results insertion. Here is the insertion. Now let's look at the performance results. For insertion of 50,000 records, the Fenwick tree was fastest at just 0.001 seconds, followed by segment tree at 0.002 seconds and splay tree at 0.0026 seconds. Among the indexing structures, red black tree performed best at 0.0118 seconds, followed closely by B minus tree at 0.113 seconds and B plus tree at 0.0125 seconds. The AVL tree was slowest at 0.0186 seconds due to its strict balancing requirements. This shows Fenwick tree is 18 times faster than AVL tree for insertion workloads. Coming to search and range. For search performance with 1000 queries, B tree achieved near 0 microseconds per query, making it the fastest. AVL tree averaged 0.467 microseconds, while red black tree and B plus tree both took approximately 1 microsecond. Splay tree was slowest at 1.994 microseconds due to its amortized cost structure. For range queries with 100 operations, segment tree and Fenwick tree both completed instantly at 0.0 seconds, demonstrating their optimization for range operations. B plus tree took 0.0196 seconds, while B minus took 0.025 seconds. This confirms that specialized range structures significantly outperform general purpose trees for analytical. Coming to the height, tree height directly impacts search performance. At 50,000 records, B minus tree and B plus tree achieved the best height of only 3 levels due to their high branching factor. AVL tree maintained 16 levels, red black tree had 22 levels, and splay tree reached 144 levels on random data, degrading to 10,000 levels on sorted data. Memory efficiency is crucial for large datasets. Fenwick tree uses only 8 bytes per second, making it the most space efficient. Segment tree uses 32 bytes. Among the indexing structures, AVL tree uses 64 bytes, red flag tree uses 72 bytes, B plus tree uses 79 bytes, and B minus tree uses 98 bytes per second. Coming to the dashboard, the project includes an interactive web-based built with HTML, CSS, and JavaScript. The dashboard displays real-time performance charts, including the insertion time, comparisons, search performance metrics, memory usage status analysis, and dataset distribution visualizations. It features color-coded comparison tables and provides workload-specific recommendations for selecting the optimal data. This is the dashboard, detailed performance results. Theoretical complexity analysis. Based on comprehensive benchmarking, I can provide three key recommendations. For general indexing workloads, red-black tree is optimal. For range query and analytics workloads, segment tree excels. For memory constrained environments with frequent updates, Fenwick tree is superior. For building cloud monitoring systems, I recommend a hybrid approach. Use red-black tree for general log storage and server ID lookups where balanced performance. Coming to the conclusion, this project successfully implemented and benchmarked 7 tree-based data structures for cloud infrastructure monitoring. I processed over 6 lakh real log records, validated theoretical complexity bounds through empirical measurement, and created an interactive visualization dashboard. Thank you.